Moving on for this discussion of standard reduction potentials, the standard hydrogen electrode can now be used to determine the standard reduction potential for each of the various reactions that can possibly occur. So for example, we put in the standard hydrogen potential and we put it with a copper strip. And in this case, the copper strip is being reduced and forming copper ions. And the anode, the oxidation, is the standard potential on the left. It's written in the standard notation here. And then whatever the voltmeter reads, that's the standard reduction potential for that copper electrode. If you put silver in there, you get the standard reduction potential for silver, and so forth. And some of them are positive and some of them are negative, depending on their relationship to the hydrogen potential. And the way this is determined is that the cell electricity, which is given at 3.337 here, is the cathode minus the anode. So in this case, with the standard, the cathode, or the total is 0.337. The cathode is the copper being oxidized or reduced to copper metal. And the hydrogen electrode is 0. Therefore, the standard reduction potential for copper 2+ to copper is 0.337 volts. Positive 0.337 volts. So a galvanic cell can be used to determine the standard reduction potential for any element. In this case, it's silver. The standard hydrogen potential is on the left. It's the anode, and it's assigned the standard reduction potential of 0. Now you see in this case, it's 0.8 volts. So whatever you see in table 17.2 in your book, that the voltage that's given is for the reaction as it is written. So if the reaction is written as a reduction, then the voltage is as whatever's in the book. If it's written as an oxidation, then the voltage is numerically the same but has the opposite sign. In the case here, as a reduction, it has a positive 0.8 of a volt. If you write it as an oxidation, which is shown in the slide here, 2Ag goes to 2Ag 2+ plus 2 electrons, then the voltage is negative 0.8. So let's look at a couple of problems, and we're going to finish the lecture this week pretty early. You have some homework both that has to do with writing the cell notation, and then also doing some of these problems as well. So what is the standard cell potential for a galvanic cell that consists of gold that's reduced? Well, wait a minute, we have to write it down first. That's gold 3+ and nickel 2+, half cells. You identify the oxidizing and the reducing agents. So how do you do this? So you use table 17.2 and you write both reactions as reductions, like this. So you have gold gaining 3 electrons to form gold metal. That's a reduction. From the book you get plus 1.498 volts. Nickel gaining 2 electrons to nickel solid, minus 0.257. Now you look at these two, and since nickel is negative, it will be the one that's reversed and oxidized. Generally, when you put a cell together, the one that has the lower value, or if one of the two is negative, then it becomes the oxidized portion. And if you have two that have the same sign, the one with the numerically lower value is the one that is oxidized. And so you write it the other way. So you write it like this. The anode then is going to be nickel, which is oxidized. And since you wrote it backwards from what was in the table, it's now 0.257. The cathode's gold. It's going to be, as it's written in the book, plus 1.498. So the overall reaction, balancing, is 2 times gold plus 3 times nickel, gives 2 gold atoms and 3 nickel ions. And what you're balancing here is the electrons. The number of electrons gained by the gold has to equal the number of electrons lost by the nickel. So you have to multiply the nickel side by 3 and the gold side by 2. So the cell voltage here is going to be the cathode minus the anode, which in this case is going to be the cathode minus a minus 2.57 or 1.755 volts. And since the overall is positive, then this is spontaneous and will occur without much difficulty. Let's take a look at another reaction. What is the standard cell potential for a galvanic cell that consists of magnesium and silver? Identify the oxidizing reducing agents. Okay. So, again, using the table, we write both as reductions. So magnesium is reduced to magnesium solid, and from the table we get minus 2.372. And silver is reduced to silver solid, and it's positive 0.8. Now you would probably write the magnesium backwards, and it would become the anode. Because magnesium is negative, it will reverse to form the anode and become oxidized. So magnesium is now the reducing agent because it's oxidized, and silver is the oxidizing agent because it's reduced. And the overall reaction, balancing again, and notice you do not multiply the voltage by coefficients, looks like this. And again, you're balancing the electrons, and it's the cathode minus the anode, or 3.127.